Hi, everyone. It's great to be here. Thank you for the invitation. And also, I recognize a number of names here, so it's wonderful to see friends. And also, I look forward to meeting new people. I did in the chat, I posted a link to our workshop materials for today. So feel free to bring that up and so that you can follow along. And then I will also share my screen. So I'll go ahead and share right now. And I'm going to, I gave you the link to the Google Slides, but I think so that I can take notes while we're working together, I'm going to actually use OneNote, and that'll give me the ability to write as we're going along here. Um, so first of all, just want to introduce myself, and Joe is partnering with me in this workshop. I uh, went to NC State in the 90s and for graduate school and got interested in physics education. And then I spent 4 years at North Carolina A&T in Greensboro, and then I spent 20 years at a private college called High Point University. And then I returned to NC State 2.5 years ago, and I'm coordinating the calculus-based physics sequence. So I have 1,900 students this semester, and I feel the weight of that. I only teach about 250 of them, but I coordinate all the sections, work with instructors, and manage most of the logistics for the course. And we use the textbook matter and interactions. And being back at NC State is giving me the opportunity to implement matter interactions on a large scale, and I'm looking forward to the challenge of integrating computation and things like that at a much larger scale. So that's a little bit about me. Joe, you want to?
Okay. Uh, I taught physics and astronomy for 30 years at a local community college. And in the summer of 1999, I got an email. Actually, I got a printed letter. They were still printing letters in those days from a guy named Bruce Sherwood, who I had never met before. And he was looking for beta testers for this new and experimental curriculum out of Carnegie Mellon, the Center for Teaching and Learning Innovation at Carnegie Mellon, called Matter and Interactions. And we were looking to change our curriculum that year. And so I decided to try it, mainly because the book was free at that point. It was not yet under contract for publication, and they were basically just giving away comb-bound uh, beta versions of it. So in the fall of 1999, uh, I started using Matter and Interactions, and turns out we were the first institution in the state of North Carolina to use it. And I think that's significant being at a community college. And my life changed. All of a sudden, I was not wanting to get out of teaching physics. I realized that there were indeed gaps in my undergraduate understanding. I wasn't imagining things, and and even some gaps in my graduate training as well. And I fell in love with this curriculum, and I don't say that lightly. It literally changed my world, so much so that I drove 3 hours from Hickory to Raleigh, North Carolina State University, to hear Bruce Sherwood and Ruth Shabai give their chalk talk uh, for their interviews for the hiring committee, and they were then hired in, I believe it was 2000. Aaron, correct me if I'm wrong there.
That's
Uh,
what I
and
remember.
that began a long period of internal development and related physics education research that led to the Matter and Interactions curriculum as it exists today. And having been a bit of a pioneer in that and having had a small role in that is something that I've always been very proud of. And I just can't say enough good things about this curriculum. And we hope to convey some of this energy, pun intended, channeling Hewitt here. Hope to convey some of this good energy as we discuss this curriculum today.
The this book has had a profound impact on me as well. I started using it in 2003 when I was at High Point University, and I was the only physics professor there. And I can tell you this curriculum hooked students on physics, and more students said we would major in physics if we could. And we actually created a physics degree program and also hired, we were up to 6 faculty when I left and came to NC State, so in physics. And so I give this curriculum a lot of credit for really being the hook to getting students interested in physics. And I believe it can be very impactful on a program. Are you seeing my OneNote document right now? Okay. So
Yeah.
I'd like for you all to introduce yourselves so I can learn more about you. I want this to be interactive as much as possible. So if you could just tell your name and then select two of these questions. Who do you teach? What do you teach? Where do you teach? How do you teach? Or why do you teach? And so I'll just open it up the floor. Awesome. I think that's everyone. If not, please speak up. But it's so great to meet people. I feel like with each person, there's a connection, and we can just have a lot of conversation. And for those of you teaching engineering students, that's my course. It's almost entirely engineering students, 1,900 students, physical science as well as engineering, no physics majors. And so this curriculum absolutely can be used with engineering students. Bob, in Baker, you mentioned you're teaching high school, and actually, I was going to talk a little bit about high school as well. So, got some
Great.
connections with that. So, I will try to, and this really is an optics workshop, and so Joe can really speak to using this into your college environment. But it really does connect with all of the different environments in which you all teach. And I read over the registration, what you hope to get from this workshop, and it's some of you have experience with mattered interactions, and some of you maybe haven't seen it at all. And so we have a pretty big range of folks who are here, and I hope that I can give you some nuggets that are useful that you can take with you, um, uh, regardless of the reason you're in this workshop. So the purpose of this workshop is twofold. It is to work and it is to shop. And so there will be times when you're working and thinking and working in groups, and then you're also shopping. You're seeing, is this for you? Is it for your students? Are there some ideas here that you could implement and find useful? And the fifth edition of the textbook is coming out in the next month. And so this is good news, Sam and Sue and others who are using Matter Interactions. As soon as it comes out, and you may have gotten an email already from Wiley, if you're on their distribution list, that you can order an evaluation copy. And I wanted to demonstrate it, and I realized I'm on a tablet computer, my PC, and I'm not able to log into the fifth edition on this laptop. I don't know my password, and so I'm not able to actually sort of show it live. But the big things that are different in the fifth edition is, and this has been 10 years since the fourth edition, is number one, it's designed for digital media. Who was it? Was it Theo talking about students seeing a print book and be like, "What is this?" This edition is truly designed for digital media. Yes, there will be a print version, mostly for instructors, but it has embedded videos, it has embedded VPython simulations that are interactive, and it has computational tutorials with Ruth Shabai walking through writing the computational models in various chapters where computation is infused into the chapter. And so that's a big difference from previous editions is this is best consumed through the Wiley ebook reader. It's even better actually than other like Vital Source EPUBs because the interaction is built into the book in the Wiley e-reader. So using that with the online homework is probably the best way for students to use the book. It's going to be much more interactive. Also, a number of the chapters have improved narrative. I don't know how many introductory physics books actually get improved in their clarity and writing and organization. And so there are substantial improvements to the chapters 2, 3, 4, 5, 10, 11, 14, 18. And these were chapters that we thought students were really struggling with in our experience. And so when you go back to the first edition Joe was referring to at Carnegie Mellon, and with each edition, it is improved in its implementation and clarity and and effectiveness with average students. And so there at one time there was a criticism that it was too advanced. It was for Carnegie Mellon students. And in fact, it's actually really been designed for average students. And Joe has taught from it since what, 99, and I've been teaching with it since 2003 in and at High Point University. And so it really is appropriate for all the different environments in which we teach. Um, and the improved support for computation is remarkable in the book itself. Frank Casey, a high school teacher from New York, had signed up for the workshop, and when I saw he had signed up, I thought, oh, I got to put this in. Frank actually took the Matter Interactions course online through NC State, and he implemented Matter Interactions in his high school class and and he wrote a blog post back in 2012 called WTF, what's the formula? and and he said he told his class that when they have a WTF moment, they've lost sight of the big picture and fundamental principles. And I think that captures matter and interactions very well. That matter interactions is about a few fundamental principles and applying those in a variety of applications. And so it really is about reductionism and about modeling, but with applying a few fundamental principles. So the focus is always on fundamental principles. And so when Joe and I talked about this workshop, we thought that we could do that by capturing sort of one idea that's in matter interactions that we think has been very influential, and that is the thread throughout the book on system and surroundings. This is, and we'll have some examples in mechanics as well as E&M. And when we're teaching students to solve problems by applying the momentum principle, aka Newton's second law, and the energy principle, we emphasize defining the system and surroundings. And so it's a big part of applying fundamental principles. Now, I'm working with a high school teacher right now from Raleigh who's taking a a course with matter interactions, and we're just working one-on-one. And when she came across system and surroundings, she actually said, "Oh, this is now a part of the AP Physics 1 curriculum." And it's, as far as I know, that in my experience in teaching, using matter interactions was the first time I encountered a consistent use of defining system and surroundings. And Joe, that was your experience as well, right?
Yeah, I'll say that in 6 years of physics schooling, I never once had to define a system.
And so, and so now this is part of AP Physics. And so I think we're seeing more and more. In fact, Bob, this teacher I've been working with, her name's Allie, and she was telling me how some other things in matter interactions, like the emphasis that little g is gravitational field, it's not acceleration due to gravity, and things like that have actually made their way into AP Physics. So there's some other related initiatives I wish we could talk about. And I'll just give you a little bit of a heads up. I'm working with 1,900 students right now and about 12 instructors. And do you ever have students come to you and say, I come to class, I take notes, but I failed the test. What do I do? And how do you reach that group of students? And so I actually started a workshop after the first test, and it's based on the book Teach Yourself How to Learn by Sandra McGuire. And if there's one thing I could tell everyone, other than matter interactions, that has the biggest impact in teaching that I've ever seen, it's this book. And it's a book written for students. It's short, easy to read, and it is life-changing for students if they implement these suggestions. And I did a 1 hour workshop. I had 140 students come to my workshop last week. And um, in 2 semesters, I now have 2 semesters of data, and students who attend the workshop improve 11 to 12 points more than non-workshop students. Now that's just students who attended. I have no idea who actually take it and implement it. But I can tell you I have students with incredible growth. And it's incredible to see students going from a 55 to an 85, a 90, et cetera. It's probably the one thing that it's one of the most effective things I've ever seen for a 1 hour intervention. And then my other passion is integrating computation into introductory physics. And about 2018, we started. I did this since 2003, but in 2018, I started actually integrating it by teaching students to write their calculations for homework and tests in VPython. And that was a game changer. Before that, probably roughly, I'm just guessing, half of my students thought that computation was not that important, it wasn't that useful, and it was just an add-on to learning the physics. And then after that, 100% of students believed they could code and thought it was important. And that is and felt comfortable doing it. I've never seen anything that effective when teaching computation. So I'd love to talk about these things more later, or if you want to email me, we could set up a Zoom call and talk about these things. But today, Joe and I want to talk about the this idea of defining your system and surroundings. And I'm going to give a brief background into sort of the physics that's emphasized in the mechanics part of the book. And just as I don't know, reminder, some of you, this is extremely familiar, and some of you are like, might be like, well, I haven't seen it worded this way before. And so I hope that it'll still be useful to everyone. But conservation of momentum is that the momentum of the universe is constant, which means it doesn't change. So the change of momentum of the universe is zero. So if you define one part of that universe as your system, then everything else outside the system becomes your surroundings. So the change in momentum of the universe is the change in momentum of the system plus the change in momentum of the surroundings. So if your system has a change in momentum, that is offset by a negative change in the momentum of the surroundings. And so that's the statement of conservation of momentum. Now, the momentum principle tells you what causes the change in momentum of a system. And so let's just begin with a particle. Here we have a particle and we define our system as this particle. So the surroundings exerts an impulse on the particle, causing a change in momentum that's equal to the net force by the surroundings on the system times the time interval. And so that is the momentum principle. And then if we write this in what the book calls the update form, P final equals P initial plus F net times delta T. Now later, when we talk about the energy principle, you see the same sort of form of the idea, the relationships. When we do energy, we'll see the change in the energy of the system is equal to the sum of the inputs to the system. And in the same way that we see the energy principle here, and we will write the energy principle in update form as E final equals E initial plus the sum of inputs. So you see this parallelism in these principles. All right. So this comes up when we are talking about calculating gravitational force. So when we calculate gravitational force on an object, that object is the system, by the other object, which is the object in the surroundings. So when we're calculating gravitational force, we define the system and we define the object in the surroundings. And that's important because we have to draw the R vector from the surroundings to the system. And then we use that R vector to calculate the gravitational force on the system by the object in the surroundings. So again, defining the system is critical to getting the direction of the R vector correct. If you don't define your system and surroundings correctly, it's maybe confusing on how to draw your R vector. Well, your R vector goes to the system.
And it suddenly dawned on me that when you go from physics to chemistry or from physics to engineering, including engineering thermodynamics, you may see slightly different definitions of system that basically include sign flips. I had a former student from UNC Charlotte bring me a textbook, and they defined this was an engineering thermodynamics textbook. And in that textbook, the system was designed such that the mass never changes. And not being an engineering person, I don't know how prevalent that definition of system is, but do be careful for subtle variations in going from discipline to discipline, variations in the definition of system, because it could be a little confusing at times.
Yet super important in those other disciplines, right? To define the system. Now, what if you have a multi-particle system? So here we have a binary star system, and we have two stars, star one and star two, and it's the pair of stars that we define as our system. Now, in this case, the total momentum of the system is the sum of the momentum of the stars. And in this case, the net force on the system is zero. So we might call that a closed system or an isolated system. And in that case, the momentum of the system is constant. So the momentum of the system does not change. So the change in momentum of star one will be equal to the negative change in the momentum of star two. And so this is a situation where the momentum of the system is constant. And often we call this conservation of momentum. But technically, conservation of momentum and constant momentum don't have the same meaning. So, for example, if we define star one as our system, then star two would be in the surroundings. And we could apply conservation of momentum that says, well, the change in momentum of the system will be equal to the negative of the change in momentum of the surroundings. But in this case, the system is both stars. And so the net force on the system is zero and the momentum of the system is not changing, which means delta P1 will be equal to negative delta P2. So that just tells us the momentum's constant. Joe, you want to uh, mention something on that?
Yeah, in the famous Blue Book of Teaching, Arnold Ahrens has a treatise where he discusses the distinction between conservation, constant, and invariance. And if you've ever read a special relativity book, you'll see such silly statements as Einstein showed that the speed of light is constant. Well, he did no such thing. Of course, the speed of light is a constant, but in special relativity, it's invariant, meaning it's the same in all inertial reference frames. And very often, the distinction between conservation, constancy, and invariance is not used, especially in introductory physics books. So it's an important distinction. And sometimes people say, well, you're just being pedantic. Yes, I am being pedantic. That is the whole point. As teachers, we a certain amount of pedantry is warranted, and this is one of those situations.
I think just having a framework that's consistent so that you don't have to undo things and go, oh, that's not quite right. That's, is I think useful and important. Um,
Question.
yes.
So could you say here that the fact that the momentum is constant is a consequence of momentum conservation?
Yes, and it is yes, I think so. And yeah, I think so. Joe, what do you think?
Yes.
The It's interesting. And so I didn't bring up Newton's third law and the this textbook refers to Newton's third law as the principle of reciprocity. And it applies, you can see it here in the gravitational force when we calculate the gravitational force on the other object, capital M here, by the small m, then it reverses the r vector and reverses the f vector and so forth, but we get the equal magnitude opposite forces. And that applies to the gravitational force, and it applies to the electric force. And in the mechanics volume, volume one, after the gravitational force, there's a section on the Coulomb force. Because once you've done this with the gravitational force, it just makes sense to do it with the Coulomb force. There's another reason that the Coulomb force is put in there in mechanics, and that is when you start to talk about contact forces, what are those contact forces due to? They're due to electric interactions between the atoms of the objects. And so it, going from fundamental forces to contact forces and describing what is tension, what is a normal force, friction, etc., you need to have established these electric interactions. And so the Coulomb force introduces that, and you get the same principle of reciprocity. But it's interesting that you can get situations, and that principle of reciprocity is used in understanding and relating this the fact that the change in momentum of star one is equal to the negative of the change in momentum of star two. But it is interesting that you can come up with scenarios such as a proton and electron, protons moving, let's say, to the right. So let's see, I'm looking at this from your side, so it's going this direction, and then electrons moving this direction. And when you calculate the magnetic and electric forces, um, they're not equal and opposite. The electric forces are, but the magnetic forces are not. So you go, well, what happened here? And so it turns out that the field itself has momentum. And so momentum conservation is more, it's at a higher level than Newton's third law. We'll put it that way. Newton's third law, what we call Newton's third law, is really the reciprocity inherent in the gravitational and the electric forces. Anyone want to comment on that? Others?
I mean, just a general comment.
Yeah,
This all is very, very, I think, really important stuff. I know that in our classes, one of the challenges that we've had is that probably like everyone else, it seems like there's too much to do, too much to cover in a semester, and there have been pressures from the registrar, from the dean before to consolidate our courses in order to
yeah,
lower the total number of credit hours,
yeah,
which means that we have done things like switch our introductory physics sequence from 3 semesters to 2.
yeah,
And one of the victims of that sort of consolidation is discussing systems.
yeah,
So we provide um, kind of secondary material. We make some videos, some practice problems. They really focus on the system concept. But I've always found it to be very frustrating because um, it is the sort of thing that gets thrown to the wayside too much.
yeah,
And whereas you can solve many physics problems without ever referring to a system, in fact, you really do have an underlying definition of what the system is anyway. But then
yeah,
on other problems where it becomes really critical to be able to define the system before you can even solve them,
yes,
that's where
yeah,
students really lose out.
yes, yeah,
So, I'm just saying that I acknowledge the issues and the importance. I'm not trying to say that, oh, there's a really good solution to this issue because I'm not actually sure that I see a good solution to the issue right now unless you get a real fundamental um, change in thinking about the pedagogy.
Yeah.
And I get, in a way, that is, in fact, exactly what you're trying to do here. So
Yeah.
for those locations that do switch over to this textbook, I think that there will be some benefit from it. Although I do wonder this, you've got to spend some time on this.
And
Really,
that's
in order to make it
yeah.
worthwhile for the
Yeah.
students, and you're going to, in a finite space of
Yeah.
time, you're going to lose other stuff.
And something like this is what's nice about this is that it's sort of foundational to everything. And so you constantly refer to system in everything you do. And so it becomes well, they will see it over and over and over and over again. And and so it's not one time, it's threaded throughout. And I think that helps. So let's take a look at this because Stefan, you just mentioned some problems. You really have to define your system. And I'd like to do this activity, and I'd like to break out into groups. And I've never run a workshop over Zoom before. I'm not taught a class over Zoom, and so I asked for some help from Chris about this. So I'm hoping to break into groups. I think it'll be random, and I would like for you to solve this problem and think about your choice of system as you solve the problem and define your system, okay? Define your system, define the objects and the surroundings that are interacting with the system, and then apply the momentum principle, aka Newton's second law. So, how does this work? I have to stop
Great.
sharing,
Yes.
and you all have the link to the Google slides, so you could pull those up so you could see them. And now we're going to go into breakout rooms. And
Yeah, we solved the problem, but we didn't use the ball spring model or the momentum principle really. So,
wait, maybe you did, but you didn't
well,
realize
I mean,
it.
it seemed kind of trivial. Um,
Yeah, yeah, yeah. We're going to talk about it. Yeah, and because yeah, I want to wait till everyone else comes
yeah.
back in, but yeah. So the question is, did you use the ball spring model, or and did you use the momentum principle to solve the problem?
Well, I mean, technically we used the momentum principle, but we didn't seem like we needed it. I mean, it didn't, you know, still used, you know, we sort of did the old-fashioned way, even
Yeah,
though, yeah.
yeah.
To show how important this concept of system is, a number of years ago, I had one of these made up. And I put this on the front. Here in North Carolina, we can have front license plates. And physics students got the joke. System equals Joe plus car. And my physics students, I mean, they're like, this guy is cool. Okay, anybody that would put this on his car
That is
and
fantastic.
drive around town in public. So
That is fantastic. I forgot you had done that. That's awesome. All right. So, what were some things? First of all, just tell me some things that came up in your group, and then maybe let's walk through the solution in the matter and interactions way. Like like all of you had the answers, but kind of what was your reasoning, or how did you go about it, or how do you think students would go about it, etc. So let's just sort of talk about it.
Well, we talked about actually using two different systems, making the ball
Hmm.
one system to get the tension at the bottom of the wire, and then the ball and the wire together to get the tension at the top. Um, with the idea also that we could have also done sort of a differential look along the wire itself, but
Hmm.
that was maybe, I think we agreed that might have been on a higher level for students. We didn't really talk about it from the standpoint of momentum, um, to be honest.
Hmm. Hmm. I think Theo, you were saying something similar, right?
Yeah, maybe we've been doing it one way for so long. Yeah, we're stuck in our tracks.
and that's important, Theo, because a lot of times we tend to teach as we were taught. And Because there's nothing moving here, there's a tendency to think, well, there's no momentum involved. And that's kind of true, but it's also kind of not true. There's momentum there. It happens to be equal to zero. So you have a static situation. And in fact, we were talking about engineering students. They take a whole semester or sometimes a year's worth, depending on the school, of courses where it's nothing but the momentum principle where P system is equal to zero. And they call it statics. Whole 1,000-page books have been written on that one application of the momentum principle, but it just sort of falls out here. And I agree. Sometimes we have to change the way we think about these things. And I know that when we talk about energy in just a few minutes, that was a huge brick wall for me when I started using matter and interactions, because even in grad school, in Goldstein and Jackson, we weren't trained to think quite this way about these things. So I agree, Theo, that sometimes we do have to rethink how we think about these things.
The um so yeah, so what everyone mentioned, uh you define your system as the ball, and what that gives you is the tension at the bottom of the wire. And then when you define your system as the ball and wire together, and I'm just going to draw this still as, I don't know how you teach students to draw your system. I just often have them draw a dot anyway. But basically you have a tension at the top of the wire, and we'll talk about this in a little bit more detail here in a second. But you go through the same process, and then the tension at the top of the wire is going to be equal to the mass of the ball plus the mass of the wire times G. So you end up getting 6 newtons. But the so I think I think was it Anthony? You, I think it was you, but correct me if I'm wrong. Were you were talking about like layers of the wire, or Stefan? Maybe you were talking about layers of
Yeah.
wire or something.
A more sophisticated approach would be to say to have the system be an infinitesimal length of the wire dy somewhere at an arbitrary location. This is how you would get the tension throughout the wire. Right. And then there must be a tension difference between the top and the bottom, a T and a T plus dt, because that's
Yeah,
what's going to give you support that little infinitesimal bit of mass that's in your,
yeah,
right, exactly.
yeah.
So I guess I haven't, I know I've seen the ball and spring model. The only thing I have a little concerned about is because you automatically want it to stretch. And of course, the wire does stretch a little bit, but
Hmm.
it's such a small amount that I
Hmm.
don't know if that's a confounding variable for students or
Yeah.
not.
So the purpose of the ball spring model in chapter 4 of Matter Interactions is to give a physical motivation for what tension is. And so they introduced the ball spring model, and then one of the first system you look at is a wire with a load hanging from the wire, and the wire actually stretches a very small amount, like a millimeter or something. And they actually do use the ball spring model to as and they illustrate modeling to determine the stiffness of an individual bond in copper for given the stretch of that copper wire. And it's a nice exercise for illustrating the usefulness of a physical model. I have colleagues who teach material science, and they love that we introduce this in the course, because they use it all the time in various ways, and they love that we're teaching modeling in general, physical models to represent the real system. But one of the reasons this is in matter interactions is so that students have a physical explanation for what tension is. And why do we even say tension in the wire or tension in the string? We're talking about the stretching of these bonds in the material. Um, And well, a string may be a little bit slightly different, but that's why we use a simple model, ball spring model. The other thing, so when you think about your system here, if you're getting the tension in the wire, you can imagine the top layer of the wire being the system that you use. And I actually like to let me grab, let's see. Um, so you all have probably done the falling slinky demo, possibly, where you hold a slinky and you let it go. But if you just hold a slinky, you can see it stretches more at the top than it does at the bottom. And so this shows you that the tension is greatest at the top of the slinky and least at the bottom of the slinky. Um, but this problem illustrates the importance and usefulness of defining your system in order to solve this problem. And this, don't tell my students, but this is a question that will be on the test on Tuesday for actually about over 1,400 students will be answering this question on Tuesday night. But let's take a look at the problem and then let's just talk about it. We're not going to do breakout rooms, but we have two bowling balls held by these two wires, and these are low mass wires. By the way, we didn't mention this, but why do we talk about low mass wires? Well, it's because what we're saying is the tension is the same throughout the wire. So when can we assume that tension is the same throughout the wire? It's when it's a low mass compared to the mass that's, let's say, hanging on the end. Um, the and so here we have two low mass wires, two bowling balls, and the question is, what is the tension in wire one and what is the tension in wire two? Now, students haven't seen this problem before, but they have seen the previous problem on homework. But how would you expect students to go about solving this problem given the previous homework problem? Or how do you hope they would solve it?
I would hope they would make a system of M1 and M2 together,
Yes,
isolate wire one.
yes, yep, exactly. Now, if they did not do it that way, how else could they solve the problem if they did M2 as a system and then M1 as a system separately?
Well, M2 as a system would give you the tension in the lower wire, and then M1 would then have two tensions on it, one from below and one from above.
Mhm.
Um, and there would presumably you would have, the idea of essentially each system gives you a separate equation,
Yep.
which you then combine together in order to be able to solve all the pieces to it.
Mhm. Mhm. And which do you think is conceptually easier for a student to treat M1 and M2 together as one system or do it the way you just described?
Good question.
Based on the kind of answers we get for a problem like this, I don't know how to I don't know how to second guess what the students are doing because compared to the first one, this one usually is quite a step up for them conceptually.
Mm,
I was going to say one thing that could be useful is that it doesn't matter which way you do it.
mm,
You're going to get three equations, but they're not all independent. And so if you get one piece of information from considering M1 as the system, one
mhm.
piece of information from considering M2 as a system, and then another piece of information which is not independent, considering them both. So you can show
Mm,
them that you can check your work that way by choosing
yes.
another system.
Yeah. Yeah.
Choosing a system is akin to choosing how you're going to organize all the various quantities involved.
Mhm.
It's an organizational technique.
Yes. And you really cannot you can't apply the momentum principle. You can't draw your free body diagram and then sum the forces until you've defined a system. And I think Stefan, you mentioned this earlier. It's sort of like it's often implied, or we expect students to do it, but it may not be something we've explicitly taught them to do.
I think in our situation, we would find a lot of examples where students would actually get the correct answer, or those students that could get the correct answer, if you then circled back around and told them, what was your system definition when you got that answer that was
Yeah.
completely correct, they wouldn't be able to tell you.
Yeah.
You're exactly right. And that's when I would say, now you need to think about the physics of
Yeah.
the situation. Well, I got the right answer. Okay, that's fine. But show me how you got to that answer. This is
Yeah.
physics class, not an engineering class. We want to know how you got there. And
Mhm.
that's when this becomes important.
Okay, I want to do another breakout room here, and I want us to do this question. It's not going to take very much time, and so I'll bring us back together after just a few minutes, but let's do the breakout rooms. And Chris, do you want to do the breakout rooms?
Sure.
All
Um,
right.
I've recreated them so we have slightly different groupings,
All
I think.
right. Okay. Do we have everybody? So, all right. So this was all right. Well, tell me about the reasoning for this one. The question asks which arrow indicates the direction of the change in momentum of the comet during the next small time interval after this instant. So, what's the reasoning, and where do we start?
Well, I started by making the system the comet
Mm-hmm.
to begin
Mhm.
with, and then used the basically the impulse principle. There's only one force, you know what the direction is. So the F delta T gives you the correct direction. When I made the system and the comet and the sun, I had to think about it a little bit more and was led to uh, being forced to think about the center of mass then.
Mm. Now that's yeah.
Your choice of system can make the problem almost trivial or almost impossible, depending on how you choose to set up your bookkeeping.
So So this question was on a test about 3 weeks ago. And that test, they had used the momentum principle, delta P equals F net delta T, over and over and over. Now, keep in mind when I say the momentum principle, depending on the situation, sometimes they're writing it like this. Okay, we did constant force motion problems. We did projectile motion. We did sort of those standard problems. But we also did what's called the iterative approach. So if you're wanting to predict the future motion of the comet, you would do P final equals P initial plus F net delta T. But F net, if you want this equation to be exact, F net would have to be the average net force. Well, what if you have a small delta T? If you have a small delta T, then you can approximate that by using the initial net force. In other words, you use the net force now times delta T plus the momentum now, and that gives you your momentum in the future. And this is called the iterative approach, and it works for small delta t. So students did this calculation with one or two or three time steps to predict future motion of things. And so that's what this was getting at. Well, as you know, teaching's
But
hard,
I
right?
I
So
have a question. I have a question about this then,
yeah.
from a physics standpoint.
Hmm.
So my first in the breakout room, I chose E, but the reason I chose that was because I guess I was sort of unconsciously doing something slightly different. I was actually choosing a larger, in my head, a larger value of time, which
Hmm.
means that we would have to deal with some average force. And so I was thinking of the comet being further along in its path,
Mhm.
and the force in this at this moment is straight up, but the force a little bit later is pointed back towards the sun. So my intuition drew me more to answer E than it did to answer B. But as long as answer E was not intended to mean straight back along the path, is that what is to the people
That,
that wrote this exam, was E intended to be a force straight back along the path?
yeah, so I wrote the question, and in fact, yes, the angles are such that answer E would be very nearly opposite the momentum of the comet.
Okay,
So,
then I would retract my answer of E then.
so I initially also thought B was, well, I thought B was the answer because I was just looking at delta P.
Yeah.
But
Right.
then we were in the same breakout room with Stefan, but then looking at the question again, you say during the next small time interval after the incident, Sean. So sometimes it can be a little bit ambiguous.
The
I mean,
and
in fact, they did say the next small time interval. I was guilty of doing what my students do, which is not completely reading the question.
and I don't dispute that maybe it is slightly ambiguous, and it also goes back to when we're teaching, we think we're teaching one thing, but what are students learning, right?
Hmm.
And we often don't know until we give a test question. And if most of the class does poorly, I actually look at myself and say, what can I do better? Clearly my students are struggling with a concept that I can teach better. Now we're talking, 1,500, almost 1,450 students are taking this test, right? And this ended up being the most difficult question on the test. 27% answered correctly. By the way, these questions get randomized so that other students had the comet going around the sun, a different orientation in one way or another, but all similar reasoning. But that was the average over all the versions of the test, so 27%. Now you could say, well, we could maybe teach this better. It's absolutely, or maybe it's the wording or whatever it is. But I think it also shows, and I give a workshop on how to learn, and I talk about the difference between memorization and application. And so if I just asked students to memorize the momentum principle here, or if I ask them, identify, here's a bunch of different equations, which one of these is the momentum principle, they would mostly get that right. But if you ask them to apply it in this situation, what is the change in momentum during the next small time interval? Well, that's what the momentum principle tells you. Like take net force times the time interval in which it acts, and that's the change in momentum during that time interval. But I agree, the fact that the net force is changing could be a complicating factor, except it is a small time interval, and students practice these kinds of calculations that included a gravitational force. Okay, they did a similar calculation for a spring force. Spring forces are not constant force. So how do you predict future motion if you had a spring force? And the answer is exactly the same way. Use the force now to predict the future momentum, and from that you get future velocity, of course. But you use the net force now to get the future momentum and velocity during the next small delta t, and it only works for small delta t, granted. Um, but for students, I think it illustrates too how you apply these ideas rather than memorize. So understanding them and applying is what our tests really are getting at. And it's not so much plug and chug. If I give them the vector for net force and delta t, they'll calculate delta b. They will calculate it. But do they recognize they need to employ the momentum principle in their reasoning in a given situation? There are other interesting questions that I did not prepare or bring up where we saw similar results on questions. It's a little bit like the FCI. You can look at those questions and go, oh, my students are going to get these right. These are very straightforward, but they're not always as straightforward as we think. Okay, so let's take a look at this. This is a question, by the way, that's going to be on a test next week. So don't tell my students, okay? Um, what we have is we have a proton, which is Q2, and it's traveling along this path near a positively charged ion. And this is a much larger mass, okay? Much larger mass. So M1 is much greater than M2. And the question is, what is the direction of the rate of change of momentum? Now, at this point, we are using F net equals dp dt. And notice it is unusual. We're not talking acceleration here. We're talking about the rate of change of momentum. So what is the direction of the rate of change of momentum? And these are both positively charged. So what do we hope our students are going to answer here?
Straight up.
Exactly. And I'm really hoping it's more than 27%. Exactly. And so there's the rate of change of momentum of the proton. All right. How about this next question? Question number 18. The Q1 has a much larger mass than Q2. So that's why we don't see it move very much as Q2 comes flying past. During a time interval delta t, how does the magnitude of the change in momentum of the ion compare to the change in momentum of the proton? And
Now you're just being tricky.
by saying it's much more massive, and it's possible. I was really just trying to explain why we don't see it move in the picture. But that is tricky. So Anthony, can you talk about why that is tricky for students?
Well, I would think because you could ask a third question during the time interval delta t. How does the magnitude of the change in velocity of the ion
Yes.
compare to the change in momentum of the proton?
Yep.
I mean,
Yep.
the two velocities.
Mm-hmm.
So this question about the momentum, of course, the change in momentum is the same because the force is
Mm-hmm.
the same. But the change in velocities will be different because the masses are different. And I think the students will easily get those two things confused.
Yeah.
And so when you
Yep.
say momentum, they don't really know what momentum is. They know what velocity is because they've been doing this since high school physics, but
Mm-hmm.
they don't really have an intuitive understanding of momentum.
Mm-hmm.
Even though, yeah, they don't. They
Yeah.
or they conflate it with velocity,
Yeah,
and they
students,
conflate it with
students
acceleration.
still are students still are under the influence of velocity. They try to follow the directions and the equations, but they'll get fooled a lot when when they see one like this where they can see huge differences in velocities, and so that'll sort of lead them like a shiny object to the wrong answer.
Mm, yeah. Well, let me ask you this. Um, uh, and this is unusual to be emphasizing momentum here, right? We've been talking a lot about momentum, and I'm not talking about acceleration and so forth. So why in question 8? So this is a really good point that y'all bring up because students automatically think of velocity. It's very concrete. Momentum is less concrete, but why do we want them to think about momentum? Like, why do I even want to emphasize that in this question?
Because it makes it easy to answer the question.
Mhm, mhm,
But they often don't see the shortcut because
mhm.
for the details are important to them. And so if they haven't picked out the M and the A and the F and the differences, then they're not going to see it. So they aren't going to trust it.
Mhm. The downside of multiple choice is that it doesn't get at their reasoning. But what do you hope their reasoning would be? If there was a follow-up question, explain your answer. What would you like that to be? Like,
Uh,
what do you think they would use in their reasoning?
I mean, I think they're more likely to use the equality of the forces, but I would like for them to be able to then, based on our discussion, make the system be both of these charges, which immediately makes you know that answer C can be the only one.
Mm-hmm.
You don't even have to think about, oh, I got two forces, are they equal or not, or anything. You just sort of jump straight to the answer.
Mm-hmm.
I want to return though, maybe I'm being dense. Can somebody tell me why do we focus on the momentum here? I'm not right off the top of my head, I'm not thinking about why that would be uh, the critical thing here.
Well, I would say is because it's the thing that's in Newton's second law.
Okay,
Mass is not in Newton's second law. Acceleration is not in Newton's second law. It's momentum.
okay.
And I think I do this when I teach relativity. Of course, these are to the more junior level students. Like I tell them, remind them that in physics one, the mechanics, we focused on the fundamental quantities were mass and velocity of our object, and from that we could derive secondary quantities, momentum and energy. But in relativity, it's much easier to think about the fundamental properties as being momentum and energy. And because those are the things that you have the equations for. And I think if we could do that in physics one, get them, and I guess that's what matter and interactions does, it sounds like, tries to hit them with, oh, momentum is much more fundamental in some sense than mass
Boom.
and velocity.
Guess what the first physicsy equation in the fourth edition is? I'll give you three guesses, and the first two don't count.
I've got the fourth edition in front of me. I'm going to cheat. I don't know. It's got
Okay.
to be a momentum. It's the momentum principle.
It's the expression for relativistic particle momentum.
Ah,
And be careful, Einstein didn't come up with that, Planck did. But that's the first physicsy equation after all the vectorial preliminaries and stuff. So special relativity is baked into this curriculum from day one. So they do see the importance of momentum as being a fundamental quantity in contemporary physics. It starts the storyline. So boom, you took the bait.
I really love this conversation because and I love what you said. P is more fundamental than V. And and by the way, I actually did originally write this question for delta V, and then later I changed it to ask about delta P. I could have gone either way. And we have homework questions where they answer about delta V, for example, et cetera. And I think someone mentioned, maybe it was Theo, I forget, that yes, if you ask about delta V, there's one more step to do. You have to think about the masses, where if you ask for delta P, that's just a single step, and you can apply reciprocity, as someone mentioned, or you could apply conservation of or not cons depending on how you define your system, you could say the momentum's constant for both particles. And so therefore they have equal and opposite change of momentum. But I
Mhm.
think the point here is that P is more fundamental than V. So if we could start with Newton's second law as F net equals dp dt, then in some cases we can write F net equals ma. And so the more fundamental way to write it is dPdt that works in more applications. And then in a subset of those, you could use F net equals MA. So I think there is a desire try to emphasize the fundamental, but yet still look at a lot of applications.
If I could
Yeah,
just jump in real quick,
yeah, absolutely.
I see a similar thing. I just, when you teach Gauss's law and
Yeah.
you get to Gauss's law and then you start doing those problems with the conductors and some are hollow and then can you figure out where the charge is? And they
Hmm.
all want to draw these elaborate electric field diagrams. And I'm like, no, 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 just you put in the Gaussian surface and you're done.
Yeah.
And I think it's a similar thing of
Yeah.
what's going on here.
Yeah.
And I love Joe's enthusiasm when he was waving his arms, Joe, man, I love your enthusiasm. It's contagious.
I'm like a virus.
Well, I hope not like that, but
Not a bad virus, a good virus.
So, and we have a few more minutes, and I'm just going to give a very brief overview, and then, and I won't go into all the details, but we'll just highlight one application probably or two. But in this, even more so when you get to energy, defining your system is critical. And so, first of all, we have this parallelism. Conservation of energy is that the energy of the universe is constant. So if the system has a change in energy, that's offset by the opposite change in the surroundings. The system gains energy, the surroundings had to lose the same amount of energy. And the energy principle is just that the change in energy of the system is the sum of energy inputs. A negative input would be an output, okay? Um, Now, the first system that we look at, and I call this the energy storyline in matter interactions. You start with the energy of a particle, and this is Joe. Are you waving your arms? I don't see you. All right. The the energy of a particle is gamma mc squared. By the way, a particle I define it as it's not made of anything smaller. Okay, so it's this very simple system. So it cannot have temperature, it cannot deform. It is an idealization. It's not made of anything smaller. So that's our point particle. And so the energy of a particle is gamma mc squared, and this is the gamma factor. Now that's the total energy of the particle. It's everything. But you can break it into two parts, an energy due to its mass called rest energy, and an energy due to motion, kinetic energy. The rest energy is mc squared, which comes out of substituting v equals 0, gamma is 1. So if it's at rest, you get mc squared. And now you can derive the kinetic energy from that. It's gamma minus 1 mc squared. And if you're working with students who are more advanced in math and you like to do an occasional derivation, I always warn them, don't drink and derive. It's very dangerous. Your equations get all messed up. But the binomial approximation is all you need to write gamma. Use the binomial approximation, and then you'll get 1/2 mv squared for the kinetic energy. It's a two-line derivation. So I don't do very many derivations. That's one I like to do. So there's your kinetic energy for low speed. So again, it's more fundamental to write kinetic energy as gamma minus 1 mc squared, but then for low speeds, we can use the approximation. So for a particle, we apply the energy principle. Delta E is equal to the sum of inputs, and the only way for that to happen is work. And you can either write your delta E as a change in rest energy plus a change in kinetic energy, or we call this the update form, E final equals E initial plus W. And both are useful. There are some questions where you want to reason in terms of deltas. There are other ones where you want to write out all your initial and final terms, cancel things out, and see what's left. And so being adept at working with both forms here is, I think, important. But for a particle, all you have is rest energy and kinetic energy. And the only energy inputs is via work. So when you get to two interacting particles, that is a pair of particles, and we can look at a gravitational interaction or an electric interaction. That energy associated with the interaction is what we call potential energy. So if I have a ball, why did I not bring it? Here we go. I've got a volleyball signed by the entire volleyball team at NC State last year. All right. So if we have a ball does not have potential energy because potential energy is for a pair of particles. And so the ball and earth together have potential energy. And another, again, all you need is the binomial approximation. You can show that the change of gravitational potential energy for displacement delta y with positive defined upward is mg delta y. So it comes from the gravitational potential energy written up here above. All right. Um, and there's a lot of interesting things about that we won't dive into, but that negative is important. And the fact that it goes to zero at infinity is very important. So we cannot just add a constant. It needs to go to zero at infinity so that if you have these particles and you move them far away from each other so they're not interacting and they're not moving, you should have rest energy only. And so that needs to go to zero at infinity.
And
But
incidentally, Bruce discovered a number of years ago that this is true relativistically as well, because if it doesn't go to zero at infinity, you lose the transformation properties of the energy momentum force vector.
I did not. So a lot of times we say you can add a constant. Mathematically, maybe, but physically, no.
You can't. The zero has to be at infinity.
Yeah. And so, okay, so if you have a system of two interacting particles, you just have another change in energy here, another term, a change in potential energy. But again, defining your system, if we have a ball and earth, the system is the ball and earth together. So finally, after we do that and we analyze all those problems, then we get to macroscopic systems that are made of atoms. And when you have a system made of atoms, then you have random motion of the atoms, and the sum of the kinetic and potential energy due to random motion is called thermal energy. There are other kinds of internal energy that system could possibly deform. And now you also have another way of transferring energy that's due to a temperature difference between the system and surroundings. You get atoms interacting with atoms between the surroundings and system, and that's what we call Q, heat transfer. Now we know students get confused about the words heat transfer, etc. I tend to be very wordy. And I just say it's the energy transfer to the system due to a temperature difference between the system and surroundings. Occasionally, of course, I do just call it heat transfer. But
Sometimes more words are better than fewer words if they are meaningful and if they prevent problems later on. So I did exactly the same thing. I eliminated the words gravity and heat, and I replaced them by these slightly more verbose.
gravitational force or
Yeah,
gravitational
yeah.
interaction, potential energy, etc. And then when you calculate work done by force is the force dot the displacement through which that force acts. And that becomes important because if you have a deformable system in some way, the point particle, well, first of all, the center of mass motion and displacement can be different than the displacement through which a force acts. So the net force dot the center of mass displacement is equal to the change in translational kinetic energy. If you treat the system as a point particle. But if you calculate the real work done on the extended body, it's the sum of the force dot displacement. And that's not the same. So that's an important factor for those kinds of systems. So when you're dealing with a macroscopic system, you now have a change in thermal energy that's related to the system changing temperature. You can have other kinds of internal energy, and then you have W and Q. So now this is an integration of thermodynamics and mechanics, but the energy principle is the same. The only difference in thermodynamics and mechanics is the system. But the energy principle never changes. And so while we give this a name, like the first law of thermodynamics, and then while we give this point particle model a name, this is often called the work kinetic energy theorem. We don't need different names for all these. It's all about what the system is. All right. So we only have time for maybe talking about one or two things. And so I'm going to, ah, All right. We have, I don't know. I think I'd like to talk about friction actually. So I'm going to jump to the end. Actually, yeah, I'll go to friction and then we'll come back. All right, because that's a fun one. So let's talk about friction for a second. In this problem, you move a block. So here's a block, and you exert a horizontal force on this block, and you move at a distance of 0.3 meters on the level table. All right. And it moves slowly, okay? So we'll assume constant speed. All right, so you do work. Uh, sorry, you do work that's equal to Fx delta x, and that ends up being what 5.1 newtons, I think. No, 5.4 newtons. All right, so that ends up being 5.4 newtons. Joules, sorry. I don't know what I'm doing here. That should say joules. All right. Now,
Also, just
that's
if this
wrong.
is going on one of your, yeah, I was going to say you need to
Yep.
edit that if it's going to.
Yeah. Yep. As you can tell, I put that together. I put these questions together pretty quickly. All right, so you do work of 5.4 joules. So this is the work done by you in pulling the box. Now, what is the work done by friction on this box during this displacement? And do we have time for 5 minute breakout room or less than 5 minutes? Does that work for you?
It would have to be quick. We're at I have 2:47.
All right. So
It would
I,
need to
I'm
be like a 1 minute breakout room.
all right. That maybe we don't have time for that. Okay. So what is the work done by friction? And you're welcome to say what you think the most common answer would be. And if you think it's different than that, what would it be?
Well, my
Be
students
the
hopefully would
same.
say minus 5.4,
Right.
probably to get started.
Yes. So what is, and I would say this is actually a fairly common question. I think you see this question in textbooks and things like that. So I think this is a very common question. So the work by friction is negative 5.4 joules. Is it right or wrong?
I'll give you a hint. One of the PDFs that I dropped in the chat directly addresses this question.
I definitely don't have
So,
time to
so I got
read
to
the
skim
PDF.
all 8 of them now.
Yeah.
Yeah, in 2 minutes.
Well, there must be something because we know that if we use the work kinetic energy theorem,
Yep.
there's no change in kinetic energy. So the total net work must be zero. So there must be something that's negative that's getting rid of our 5.4 joules of work. I don't know what it is. We could call it friction by definition, but I don't think that's the point of view of matter and interactions.
Mhm.
So
So
we have to take into account both the table and the block heating up, and so that's the complication.
that's the complication. That is the complication. If our system is the block, well, it is impossible for this to happen without the block warming. It has to warm it. Whenever there's friction, there's warming. And so if the system is the block, this block is made of atoms. And so when we apply the energy principle and we say delta E is equal to W, well, we can write this change in rest energy plus change in kinetic energy, but this is made of atoms now, so we need to include thermal energy. And we can assume there's no heat transfer from the surroundings. So we could set that equal to 0. And there's no change in rest energy. There's no change in kinetic energy. And so the change in thermal energy here has to be equal to the work done by me as I pull on this block, plus the work done by the table, which would be friction. And so the problem is those cannot add up to 0. And so the work due to friction has to be, and the change in thermal energy has to be positive. That's the other thing. This has to be positive. And so therefore, this work done by the table has to be, it's negative, but it's not 5.4 joules. Not negative 5.4. I'll say it's greater because it's closer to 0, but it's not equal to negative 5.4 joules. So that is the paradox. And how do we handle this paradox? Well, one way that I handle it is sometimes I ask the question, what is the change in thermal energy of the box and the table? And so what's the change in energy of the table and block system? So now if you define your system as the table and block together, now that is a closed system. Now, well, it's not closed because I'm doing work on it actually, but there's nothing else other than me doing work. So we'll say that. And so now you have the change in the thermal energy is equal to the work done by me, which would be 5.4 joules.
And I have had rather heated, pun intended, discussions with engineering students who stand me down that the work done by friction is that negative 5.4 joules and that physics is just wrong because in their engineering classes, this is what they call that quantity and this is the number that they calculate. And so I tell them, well, you can call it whatever you want, but if you look at the detailed discussion in Matter and Interactions and in one of the papers that I dropped in the chat here, you'll see that the notion of work done by friction is very much ill-defined. So we're replacing a microscopic quantity with a macroscopic quantity, and they're not really quite the same things. And I have also pointed out to students that notice how beautifully thermodynamics just emerges from classical mechanics. And again, in all of my undergraduate and graduate studies, I never saw this butterfly emerge from the cocoon. Pardon the language there, but that's kind of how I think about it. I never saw it. I mean, thermodynamics was a god-awful course involving partial derivatives. It wasn't something that fell out of classical mechanics like this. And this helps students who have had chemistry. There's a lot of thermodynamics in chemistry, and this sort of helps solidify the thermodynamics that they would get in an intro chemistry course. Once you account for all the sign flips for definitions and things like that.
And so the question is, well, wait a second, isn't the frictional force opposite the force I'm exerting? And yes, it absolutely is. That's true. That's from the momentum principle. And so, but the difference is the frictional force does not act through the same displacement as the center of mass displacement of the box. On a microscopic scale, the displacement through which the frictional force is acting is different than the center of mass displacement. And so, what if we apply what's called the work kinetic energy theorem to this box? Well, this is called the point particle model. And when we treat things as a point particle, it's not made of anything smaller. It's not made of atoms. And so it cannot have thermal energy. And so it only has a change in translational kinetic energy here. And when we do that, we do net force dot center of mass displacement. And so now we get zero equals zero, and it actually does make sense. It works. It's not very useful, but it works. So this is kind of mind-boggling when you first encounter it, and I promise the way we presented it here is not exactly how students see it. Students are led, they're led, but also, inspired, if you will, and they have activities and clicker questions in class, and so they're doing this in an engaged way as much as we can do. But they do walk through this, so they're not presented it all up front like we've talked about. They walk through it one step at a time to build their understanding and construct it. But with that, we're basically out of time, and I know that probably Joe wants you to fill out um, the the survey. But would you all just provide, and I'd love to go around each individual. I know that we weren't able to hear from everybody all the time. So would each one of you just sort of give a brief synopsis of, I don't know, a nugget, something you can take away and find useful?
And while we're doing that, Aaron, take your screen down and I'll put
Yep.
mine up and I'll put the evaluation link up there.
So if each one of you could just let me know what's a nugget that you found useful.
Well, to me,
I've never that problem with the comet was really using the delta P delta equals F net delta T is such a great shortcut. So I definitely liked, being able to use that. If when I'm crunched for time, I often don't do the impulse. I don't talk about impulse in class, but yeah, I can see that it's very important.
I would just say that it's nice to have a resource that focuses on it this way. I know that we are slowly moving away from, the paid model. So we've been using, Knight's book, but there's a lot of pressure to kind of move to, the OpenStacks. Um, and I mean, Matter Interactions is not free in that sense, I guess, but uh, it'll just be good to have that kind of resource that focuses on systems.
Mhm.
I think it could be kind of a, it could make it a strong contender for, switching textbooks. Because I don't think the OpenStacks, to me, when I've looked at OpenStacks, it seems pretty traditional. Doesn't really have the strong focus on systems. Uh, I mean,
It's
Knight,
not always
Knight,
better.
the reason we chose Knight was he had one of the better discussions of systems that we
Mhm.
saw,
Mhm.
but it still just occupies a very small amount of the book, and it's not permeated throughout the
Yeah.
book.
Yeah. Others?
Well, I guess for me, it's just a reminder to be extremely precise with my language. And
Mm.
I forget that all the time. And then after a class, I'll realize, oh, that was very sloppy.
Mhm.
And then in the next class, I have to change, have to say, remember what I said last class? Well, what I meant was, and precision is so important.
Mhm.
I think I'm going to add systems and my presentations, and uh, I think I haven't done that in the past at all.
Mhm.
And for those of you in a two-year college environment who think that this may be beyond your students, it's not. My students were as average as any other. And My students, when they transferred to NC State, were being hired by Sherwood and Shabai to be the in-class learning assistants for certain sections. I have a theorem. All students are equally confused no matter which textbook you use. Now, it's one of those theorems that I can't prove mathematically. I just assume it to be true from day one, proof by assertion, I guess. But don't think for a minute that your students aren't capable of this kind of reasoning, because I guarantee you that they will shock you. And this approach may make you realize, wow, if I had been doing this all along, students would not have been complaining about intro physics. Maybe this will be the thing that makes them see the light. That was my experience. I routinely had engineering students from Georgia Tech and NC State come take matter and interactions over the summer before I stopped teaching during the summer. And they said all we were taught was how to calculate the numbers. And by the way, I mean no disrespect towards NC State or Georgia Tech. Those are very fine institutions. But they said we never had to think about the internals before. And they said this model gave them that framework for doing that. And I think that's kind of profound. Getting students to, if students aren't understanding something, make them think differently about it. And that's what MNI does. It's not harder, it's just different. And I practically guarantee that your students can do it.
It's different, but yet it does cover the main things that people need to cover. So you will cover what the engineers need, I promise. But it's 3:01, so I just want to say thank you for coming to the workshop. I really enjoyed meeting everyone. I would love to follow up with each individual, and if you have any questions about implementation, uh, I'm happy to answer your questions, and if you want to talk about the workshop that I do or integrating computation, I'm happy to do that too.
And feel free to contact me uh, if you want to talk about this. I will do other workshops for your department or for your students. I'm an evangelist for this, and I have no financial stake in any of this, although we did co-author the solutions manual. But this is a great opportunity to get students excited about physics.